Hello there, guys. I'm sorry for the last time. Actually, my laptop was means the battery was not fully charged, so this time around there won't be that problem again. So let's start where we had left off, right? So let's take a pen and start from that osmosis diagram that we had done in the last video, right? So let's draw the diagram again. This is chamber A and this is chamber B. So what I had said that suppose this is filled with water, right? And there are particles in both chamber A and chamber B. Chamber B has many particles. So what are the inferences that we had drawn? Let's take psi W, water potential, for example, of A is greater than B. Okay. Diffusion pressure, what I had said, relate it with psi W, right? So this will also be A is greater than B, and DPD, diffusion pressure deficit, right, is nothing but the reverse. So A has less diffusion pressure deficit than B. So the equation which we will be focusing on is this one, right, this time around. So as per diagram, what we can see that psi W of A is greater than B. Now I'm going to write some statements, but before that I just want to give some clarifications. Okay, now psi W equals psi S plus psi P. Oh my god, that thing just went. Okay, I don't know how to remove this alright, guys, so I'm just going. Oh, it happened again. Okay, sure. Then this is psi P. Okay, just ignore these two because I cannot seem to erase it, or maybe I can. Wait, give me a minute. Oh, leave it. Oh, it's not. Sure. Yes, I can individually select them. And can I? Yes, I can. Okay, just for aesthetics. Okay, so what does this imply? When I write psi A, psi W is alright. Psi A is greater than psi B, which means psi S. It's happening again. Wait a minute. So into shape. This is actually a good feature as well as things like this happen. So okay, so psi S of A plus psi P is greater than psi means psi S plus psi P of B, right? Now, can you tell me a thing? I have told you in I guess video number 1 that the value of psi S is what? Always negative. So can we come to a fact that psi S of this? So can you let me just write it. Can you tell me that when I write psi W, psi W of A is greater than psi W of B, can we as well put this statement as psi S of A is greater than psi S of B? Can you tell me why? We are talking of only numerical values, guys. So when I write this, suppose I say this is -1 and this is -3. Okay, here I am taking the solute potential as -3. I am leaving this out, just forget about this. Okay, I'm just taking its value as null. Okay, so -1 is greater than -3. We know that, right, guys? So can we come at this inference? Now you can again check that. Wait, that B here, our tank, the chamber B has more solute. So now solute potential as solute concentration increases, solute potential becomes more negative. So I think it is clear that when I write, I'm writing it again, that when I write it as this, that psi W values of A is greater than V, we can as well write that psi solute potential of A is greater than V. Why? Because mass -1 is greater than -3. Alright, this is a concept. And I will also like to write this statement that the value of psi s of A is less negative than that of psi B. I hope this is clear to you all. Like, this is the only thing that I wanted to infer from this. Like, I don't know what, like, this is like just a language quest, nothing more. Okay, so I just wanted to put this out so that you can see a diagram and you can come to a conclusion that this is what is it, this is what is happening. All right, so now let's again take a diagram. So do you know what is the end result of osmosis? What is the end result? Right, right. So the solute, let's go up again. So let's say solvent goes from here to here, then what is the end result? What is the end? What happens in the end? Well, in the end, there is equilibrium. So let's see that, let's come to that conclusion via a graph. All right, let's come to that conclusion via a graph. Let me make a graph for you. I'm sorry for my lines here. Sorry. Okay, that was straight. Anyway, so let me write, let me use some, let me use green. Initial, and let me use final statement. Okay, and let me just draw down. Okay, this is a graph. Let me use the red one, psi W. This is 0, okay, and this is positive, and this is negative. So let me just use a white pen and write that psi, that psi W, right? Psi W of initially what was the condition, that A is greater than B. Are we clear? We clear that psi W A. Okay. Let's put it in graph. So similarly, you can put it as -1 and this as -3. This is just imaginary, guys. Don't need to concentrate on the fact. I am just explaining the position that I'm putting these two boxes in. Okay. So let me write this as psi water potential of A and this as psi water potential of, I'm sorry, psi water potential of B. Okay. Now finally what will happen? Let's give the final value psi dash. Okay. Psi dash water potential of A will be equal to water potential of B, and which implies that psi dash A minus psi dash B is nothing but 0. And if we come to the graph, then let's say we have a middle value. Let me take the blue pen, and let's say that this is -2. Okay, they will meet in the middle, like that's pure math, like basic math. So what will infer that these two boxes will then be at same level. All right, once water potential will slightly decrease, once water potential will slightly increase, which will lead them to a dynamic equilibrium. That is, at equilibrium, it's not like that water flowing will stop, but equal amount of water will crosses from both the direction. Okay, now the dynamic equilibrium concept is, I guess, from chemistry, but since like it's all jumbled up, but it's all right. All right, means it's all true. Don't get confused. If you are confused, just leave that part. Okay. Now let's draw inferences. from the graph. Okay, so inferences at equilibrium. There is no, just see the word I'm using, okay? Net movement of water particles across the semi-permeable membrane. Okay, have I mentioned it as semi-permeable membrane here? If I haven't, please. Okay, I forgot. I'm sorry. So, right. Okay. I think it's my mistake. Give me a moment. Yes, this white line that is in between these two chambers. Okay. Okay, I'm making it a bit thick. This is semi-permeable membrane. Okay, semi-permeable. Forget about the selectively and differentially permeable membrane. They are type of semi-permeable membrane only. Okay, come on. Now, what is the second inference? There is no net movement, and this is the first. Let me number it. And number two is that free movement of water particles. That is the dynamic equilibrium thing. Free movement. Water particles. That is, you can represent it as this sign means. In the question, this sign may also come since equilibrium is dynamic in nature. Is let me just use this code word. Equilibrium is dynamic in nature, right? That is it for osmosis. Now, let's go to the next topic that we have at hand. That is osmotic pressure. Yes, and this is the same thing that everyone is going to study in class 12, or some of you might already know. Raoult's law and all those colligative properties. Yes, this is the same thing. I will represent it as OP, or sometimes it is also represented as pi, alright? Just this is not very popular, so don't get confused. This is pi, okay, pi 3.14, yeah, that pi. Yeah, so it is the maximum. Just don't focus more on the definitions, though all the definitions are exactly perfect. Means I can tell vouch for them, they're not wrong. Alright, so I have that much faith in what I'm writing or what I'm saying. Okay, I'm just a student like you guys, and thanks for watching. It is the maximum pressure developed in a sorry, solution when it is separated from a pure solvent using a semi-permeable membrane, okay, SPM, semi-permeable membrane, or the most popular definition is, reverse osmosis and making hard water potable concept. Yes, that concept exactly. The pressure needed to stop osmosis. Which side is this pressure applied? Yes, that will be the question for today. Let's see. Now here let's come to some formulas that you will encounter in physics. Pi equals I, this is what? Dissociation constant. C is the molar constant, R is universal gas constant, T is temperature in Kelvin, right? C is, let me correct this. Don't ask. It might mean like it's very unpredictable, right? So let's just study some things, right? So I will just write it as dissociation constant, Vanta factor and all those is for chemistry. If it comes in, okay, just let me, for correlation, you can just go through the chemistry part. It is exactly that. Okay? I can vouch for that. This is molar constant, molar concentration. This is universal gas constant, and this is temperature in Kelvin, right? Now, for any non-electrolyte, I should I say? Let's just go for it. It's just 2 lines, There is not much to learn here. This is, if you want to skip, you can just skip. It's a part of chemistry, okay? That, well, once in a blue moon, they can just go for it, since, well, osmosis is there. What is wrong in osmotic pressure if it comes? So, what is I, value of I? Now we will go for 2 for non-electrolyte and for electrolyte. Okay, so for non-electrolyte, any non-electrolyte, let's say glucose, let's say sucrose, take the value of I equals 1, and for an electrolyte, I equals the number of entities that the compound will dissociate into. Depends on number of entities. Alright, so suppose I take NaCl. If I drop it in an aqueous solution, what will it dissociate into? How many entities did it break into? Can you please tell me how many entities did it break into? Well, here's a 1 and here's another. So the value of I for NaCl is 2. Yes, it is that simple. Don't let anyone fool you. And I'm not coming to the concept of association and dissociation. For this concept, you should refer to class 12, chapter 2, I guess, solution. It is simply not a part of this, so I won't go into details. There are 2 formulas, I equals I minus I minus 1 by n minus 1, and the other is 1 by n minus 1, that in place of n minus 1 it will be 1 by n minus 1. First one is for dissociation, second one is for association. Let's not go into that intricacy. Just concentrate on the simple stuff. For example, can you tell me for MgCl2? Yes, it will be 3. Let's go for Al2SO4 whole thrice. What will this break into? Okay, let me not use this. Let me just use this aqueous. So 2Al 3 plus 3SO4 2 minus. So what does this come as? Here the I comes as I. Yes, it is that simple for now. Forget about this. Yes, this is not a part of biology to be concerned. In biology, if we study for maths and all those, we keep the stuff very simple. There are some, yes, this bio chapter is related to maths in some ways, because as you can see, there are terms, there are like, when you see the terms like osmotic pressure, like there can be asked some question, because it is very basic, right? This is, what is this? This is just a formula. So everything is just based upon this, that pi equals I into CRT, right? Take this here, small CRT. It's just one formula, okay? Don't fear, guys. If you don't want, please just go through this and you will be done. Alright, for bio at least. But for the chemistry part, you will have to study this in details in chapter 2, class 12 solutions. Alright, no need to fear, it's alright. Now, let's go to some more details. Now, OP is what you see I've written here. Alright, don't tell I don't have. Osmotic pressure. Osmotic pressure. Here is the interesting part, guys. Don't miss. Is the negative of osmotic potential. What is OP? Osmotic pressure. I am just writing this, okay? Osmotic pressure, and this is what? Osmotic potential. Okay, and don't forget this. Very well. Let me tell you the stuff that I am going to tell you next. If you have any problem understanding, please, you don't have to go through it, okay? It's not that important, but if you know it, it's for that extra edge. You know, this is osmotic pressure. I write osmotic pressure as OP, okay? And let's say we write here osmotic potential, psi P, okay, or solute. I'm sorry. Osmotic potential. Should I do it? Oh my god, I have made a mistake. I'm sorry. Yes, yes, yes. So I was going wrong. Okay. So osmotic pressure and solute potential, which is also called osmotic potential, solute potential, osmotic potential. Let me just write that. If it is too confusing, please leave this part. This is my only suggestion for this part. If it is too confusing, please leave it, else you can as well go through. So how can we define this? This is pressure to stop osmosis. You might even find this points to be like, how is this coming? If you have any question, just leave it, okay? And this is what decrease in free energy of water due to addition of solute particles. If you have any questions, please just leave this part. This part is not worth that much attention, but this is those extra edge topics that they might once in a blue moon they ask. So yes, inside a plant cell, right? And this develops both in confined space, SPACE, and also in an open system. For example, what is the example of an open system? Beaker. Salt solution in a beaker. Okay, the one diagrams I was drawing. And confined space is this plant cell. Okay. And then number 3. Okay, so its magnitude. Magnitude is same, but opposite sign. Okay, So this is a don't, it's just a point. You can as well just stop it here. But I know this may be a bit awkward, but it is what it is. So what is the only takeaway? That the major fact is that osmotic pressure. What do we need to know? That osmotic pressure is negative of psi s. This is a good fact that we should remember. And what is the definition? Remember the definition and that 5 equals CRT. That is all. If you want to leave this chart and all, might as well. But be sure to remember this thing. Okay. Come on, let me see how much time we are recording. It's 25 minutes. Let's go. 5 more minutes and then let's see you guys in part 5. This is part 4. Okay. So let's go with reverse. Oh man, my spellings are getting worse. Reverse osmosis. Okay. So what is the definition of reverse osmosis? You just need to know the definition. These are all basic terms, guys. It is expulsion of pure solvent, that is water from a solution. When does that happen? Confined in space by the help of an semi-permeable membrane. Okay, by applying a pressure that is greater than or equal to the osmotic pressure. So from this statement, what do we come to know? That I didn't write that. Osmotic pressure on the solution side. Okay, on the solution side. So what do we come to know? As I've said, greater than or equal to. Osmotic pressure is the minimum pressure, and with which side? On the solution side, right? And the fact that it is bounded by an SPM. This is known as reverse osmosis, and it has one function alone. Means one of its popular uses. Its use making hard water fit for drinking. So I can give you a tip that I used to do. Let's say for this part, I come across hard water, right? If you guys remember in class 11, okay, I'm writing it inside, class 11 chemistry, in the chapter hydrogen, right, we study of all those methods, how to make temporary hard water, permanent hard water, right? For example, say bicarbonates and I guess sulfates and chlorides. I don't remember this. Bicarbonates was there. Sulfate, or was it carbonate? Oh, let's skip this. Bicarbonates was there, I hope, yes. So no, let's just skip this also. So say for some anion radicals, water was made hard, right? Now there were methods to convert temporary hardness of water and permanent hardness of water. So what I can give you the tip is that suppose you were revising this and you come across this part, that is hard water, then what you might as well do is just go and see in class 11 book these parts, the not much, see the anion radicals that were used to make water temporary and permanently hard, and the methods that one can use so as to get rid of the temporary and permanent hardness, as questions from this have been. Means one question can be asked from this part only, means hydrogen part. The part at the end is more important, I think, than the whole chapter itself actually. So Clark method, then synthetic resin method, permuted method. You guys can go through it when studying this part. I used to do this, and I think it has helped greatly. So let's go with then Turgor pressure. Oh wait, let me just see the time of recording. If it is over 30 minutes, then I'll just do it next. Okay, it's just 30, so let me just go over the Turgor pressure. Is actually just one line. Okay, Turgor pressure. These are just basic terms, guys. You don't need to even study this much. I'm telling you all because it might just give you the extra edge, but this is all you need to know. That Turgor pressure is equal to psi p. Yes, pressure potential is almost equal to pressure potential. So let's just tell me what is the definition. I don't need that. What is the definition? Pressure built up in a cell. Pressure built up in a cell due to osmotic entry of water into it. This is it, nothing more. And let's just, since we're doing this, let's just do another basic, what do you say, basic term, wall pressure. It's related to Turgor pressure. So wall pressure. So you can see in NCERT that these parts are mentioned but not very clearly. So that's why I'm giving it in a bit clear fashion. Wall pressure is WP. So what is wall pressure? So this is the pressure that actually counteracts Turgor pressure. Okay, this pressure counteracts the Turgor pressure. Now let me write the definition that when Turgor pressure builds PS up in a cell. Okay, then the cell wall. Why does Turgor pressure builds up? Due to osmotic entry of water into it. So just written here. Just written here. Osmotic entry of water into it, right? Turgor pressure builds up into a cell. Right. The cell wall. The cell wall exerts an equal but opposite pressure. But let me just write it in green. Equal but opposite pressure. Equal but opposite pressure to that of the Turgor pressure, and this is called what? The wall pressure. So can you find, do you know what definition I'm going to write just now? Well, you probably have guessed it, but it is that wall pressure is nothing but opposite of Turgor pressure, which is nothing but this. Okay, that is it for this. So I will see you guys in part 5, and thank you for watching. If you have liked it, please do the needful.